So it is the first time I'm in India. I'm really impressed. Thank you very much for the invitation. It's a great pleasure and honor to be here. I'm going to offer some kind of crash course in stochastic analysis with, for diffusion with jumps. This is called stochastic climate models with Levy noise, because the group where I did my PhD in Humboldt was motivated by a certain kind of data set, which actually looks very, very rough. These are data from the last ice age. They are temperature proxies, which are fluctuating very, very much. And climatologists, and especially in Copenhagen, were proposing that these kinds of models should be well modeled with kind of diffusions, which expose some kind of very non-Gaussian behavior. So what they did is they made some analysis of the noise. So first of all, here is the data. There are temperature proxies. The temperature proxies from a spot in Greenland over the last 90,000 years. They're fluctuating very much. So this was the mathematical point of view to start modeling and to start thinking about it. What the climatologists did, Ditlevsen in Copenhagen, they made an analysis of the noise, especially of the increments. And here you can see some distribution, some cumulative distribution of the actual state. And then you can look at the distribution of the increments in these kind of data. So how do we come from one point to the next point? And you see something which is, so this is a plot we did, and these are the slides from the original paper, and they made an analysis of the distribution of the increments and an analysis of the frequency of the waiting times, and they looked rather linear, what they had here, and this is something actually rather very non-Gaussian. So this was a motivation to, and what they proposed, to model these kind of data as a dynamical system, maybe a bistable system with some kind of noise. So the noise they proposed should be non-Gaussian, should be some kind of power law, and the basic model should be something like this. You have the time derivative should follow some dynamical system, and the noise, which should be stationary, it should be centered, and you have delta correlation. So this is the whiteness actually of the noise. But of course, pardon? This means the distribution should be equal. Yes, should be independent of time. So this is the basic motivation. And so in the case that you have a Gaussian vector, the delta correlation, of course, implies the independence of the increments. So the independence of those. For non-Gaussian vectors, of course, delta correlation does not imply independence. So uncorrelatedness does not imply independence in the case of non-Gaussian vectors. Instead, what we're interested in are ID non-Gaussian vectors. And here I want to make the bridge to the models, actually, I would like to study with you. So instead of looking at these kind of models where you have actually Gaussian noise, you look at the integrated version of these. So you look at integral equations with some kind of processes here. And these processes should be processes which, first of all, okay, starting in 0, which have stationary increments. So instead of looking at the actual distribution, that they should be stationary, you look at stationary increments. This means that the increments you have in time should be proportional in some sense to the time increment. We'll see what this actually means. And you assume that all kinds of increments, all finitely many of those increments should be independent. If you are in front of such an object, then you're in front of a Levy process. So this is the reason why Levy processes actually are, so roughly why they are interesting for me. And we will, in this first lecture, in order to get acquainted with all these notions, I will talk about a little bit about the step coming from here to there. This means I'm going to talk about limit theorems. So why I am interested in these kind of Lévy-driven systems is, first of all, with these you can develop new statistical tools for model selection. You have, as you have seen, you have this kind of data, and you're looking how close or to which kind of models are these data actually close. So this is something I did with collaborators, and in the second week I'm going to present you a method how to do this. So what you have to do in order to do this is to create a good notion of distance between empirical distributions and the proposed model. And the second thing why I'm interested in these kind of models is that they exhibit mathematically interesting dynamics. So these are Markovian systems, and from a mathematical side, many things are actually to be done and new. For example, first exit times are something which is very interesting and has to do with especially heavy tails, metastability, concentration of invariant measures, and Lyapunov exponent, etc. So there's a lot of dynamical features which are actually so far from the mathematical side not clear. There was a question, please. Yeah. Yeah. Well, in some sense, yes. So what we can do is we have a class of models, and within the class of models we can choose the closest one to the data. So this is kind of some kind of projection. You have some a model selection procedure. Of course, this is not a physical explanation what kind of mechanism is behind this. This is a statistical explanation. Okay. These kind of course, these noises are not something absolutely new. So of course they are systems which are noises which are actually very well known. But I think, for example, to my intuition in the climatology community, it is not very well known so far. They live very much in a Gaussian paradigm, and so this is what I would like to offer you the tools to work with these kind of diffusions. Okay, so it's not one parameter, it's actually you're comparing distributions. So comparing distributions means that you're comparing objects in an infinite dimensional space. So it's not one parameter, but it's something in a very large space. So it's the space of parameters is very, very big, you can say. Okay, you can say the space of parameters is, of course, determined by the data available, of course. Okay, so having said this, I would like to start with something rather elementary in order to get acquainted, back acquainted to probability. This afternoon, I would like to offer a course, or at least some kind of tutorial for all those who think they need some kind of help in these, in notation and basic properties at 2:30. I think it's going to be here. All right. So what we would like to do is to connect these kind of properties of n dot to n, and in order to do this, we talk about limit theorems. And I will give a brief overview of limit theorems. I hope you know. If not, then you see them for the first time. But I think it's something rather instructive. So I think the the easiest way to come to limit theorems is you have some kind of, well, first of all, we always have a probability space. We have some Bernoulli random variables. Bernoulli, they are independent. So, and of course, we're looking always at the sums of those, and then from k from 1 till n xk. So of course, we know this is binomially distributed. If the Bernoullis had some probability to have 1 with probability p and 0 with the probability 1 minus p, then we have the binomial distributions b and p. And of course, well, with the usual properties, being just being n over k, and here we have p over k, 1 minus p, n minus k. Okay, so the classical thing. Of course, expectation Sn is np, and the variance is np1 minus p, 1 minus p. And if we recenter those, well, no, first of all, so the first limit theorem actually, which you might encounter, which maybe is the most elementary one, is Poisson's limit theorem. So what do we have? If we have some sequence Mn, by the way, can you read this? So if there are problems about reading, this should not be the... Okay, a little bit larger? Okay. So if you have some sequence in the natural numbers, and Mn should tend to infinity, and we have some sequence Pn in 0, 1, and well, the Pn's will tend to 0, and there is some lambda, maybe larger, lambda in 0, infinity, such that Mn times Pn tend to lambda for n till infinity. Then we have some kind of thinning. So the Pn's are getting to 0, so with the rate of lambda n divided by Mn. Then we have that the binomial distributions n till infinity, Mn, Pn, of some fixed k. Well, of course, so we have this expression here with Mn and Pn tends to a Poisson distribution, exactly with this parameter lambda, lambda divided by to the power k, k factorial e to the minus lambda. Okay, so this is one of maybe the first limit theorems, Poisson limit theorem. Limit theorem, which you can actually have. So the proof is very elementary. So what do we have here? We have Mn by k times Pn to the k, 1 minus Pn to the k. So what do? We have Mn divided by m factorial, Mn minus k factorial. Here we have Pn to the k. And here we have 1 minus Pn to the Mn minus k. Okay, so this we can just rewrite. So this is m times m minus 1 until m minus k plus 1. Okay, and here we have Pn to the k. So each of those multiplied with the corresponding Pn should approach always mn, should approach lambda. And what is remaining, here we had some 1 over k factorial. And here we have this term, this is 1 minus, and here we can extend this with mn, pn, elevated mn divided by the same quantity, 1 minus mn, pn, mn to the k. Okay, so we don't need to expand this here. So we have here pn. Okay, so everything, so mn times pn tends to lambda. Mn minus 1 times pn tends to lambda. So this tends for n till infinity to lambda to the n, lambda to the k, pardon. Lambda to the k. Each of those multiplied with those. We have k of those. We have here k factorial. So this here is nothing but the formula for the exponential distribution. This term here tends to lambda. So we have e to the minus lambda. And this here are only k of those. What is running is n. Pn tends to 0. So this tends to 1. So we are in a Poisson regime. Please. Oh, it's a binomial. B and P is the binomial distributions. Distribution on, okay, so this is, pardon? So this is B and P of K. It's Bernoulli? Oh, okay, so this means this is 1 minus P with Dirac in 0 plus P times Dirac in 1. So probability to have 1 is P, and probability to have 0 is 1 minus P. Okay, so far so good. So the interesting thing is that we can see this, that we can rewrite this theorem as the limit in distribution. We have that x1 plus xn. And actually, those here in this setting will also depend on some n, because in each of those generations, we have the parameter Pn is nothing but the Poisson distribution with some parameter lambda. Okay, so what I'm going to emphasize is that we have here a double sequence of, in each of the parameters n, we have an independent sequence, and the sum of those tends to something which is a Poisson. Okay, maybe the most important limit theorem is then the next one. It's just one thing about the Poisson distribution. If we have the Poisson distribution to random variables, let's say x and y, and they're independent. So we have x Poisson distribution with some lambda 1, maybe x1, Poisson with some lambda 1, and x2, Poisson distribution with some lambda 2. They're independent. So this is my sign for being independent for two objects, okay, for two random variables. Then x1 plus x2 is also Poisson distributed, but with the sum of those intensities. This will be something very, very important, and we're trying to get behind the notion of what this means. So, other questions about this? I think should be rather elementary. Are there? So maybe another, but notation, everything clear. Please. Yeah, for each, no, first of all, this is for each k. Well, for well, okay, but not easily, because for any fixed n, we have a binomial distribution, which means we have beyond the value mn, we're 0. So we're with 0, and then we're just going to the value. So it cannot be uniform. Okay. More questions? So the next thing is, of course, the central limit theorem, or at least the easiest version of it, the De Moivre-Laplace theorem. And here we see something similar, at least structurally similar. So once again, we have, okay, I just shouldn't have erased this, xn. Once again, we have Bernoulli, independent Bernoulli random variables, and with some parameter p. Some parameter p once again, and we look at S star n, nothing but Sn minus np divided by the square root of np 1 minus p. So this is the root of the variance, so the standard deviation, expectation. So we have the recentered and normalized random sum of those Sns, of those Sn, the sum of the Bernoullis. And then, of course, the law of Sn star converges as n goes to infinity in distribution, so maybe right here, to the law, to a standard normal. Okay, so what we get is, so the proof of this, of course, is there are some kind of elementary proofs, but I think much more intuitive is why this should be true, and it's here. So if you have this, well, sorry for the quality of those paintings. If we have the case of p1/2, you can see that we have something perfectly centered in 0. It's a Bernoulli distribution, a binomial distribution on certain values. Those values are here. Pardon? L, okay, L means law, the distribution. So if you prefer, I sometimes write this. Okay, the distribution of this. So the values star is the definition of this. Sn is nothing but the recentered and normalized. Yeah. Okay, so this means the expectation of this is 0 and the variance is 1. Okay, this is the idea of it. So if we have this, and then you can see why these, or how this approaches for increasing a step size n to something which already looks closely to a normal distribution. So I write down maybe so this is De Moivre-Laplace. This is the easiest version. Okay, then, so coming from this, so here we have only toss coins, 0 or 1. So this, of course, is true in a much more general setting. So central limit theorem, the classical version, which should be taught maybe in probability courses, I guess. So we have some sequence of xn, or I, D. So what does it mean? This means they are independent and identically distributed. This means the family of those random variables is as a family independent, not only pairwise, but really as a family. And they all have the same distribution. We assume that they have second moments. The expectation, which should then exist, we call, or xn should be equal for all of them, should be m. And the variance, sigma squared, the variance of xn, so also independent of n. Then we have that Sn minus, well, first of all, maybe we should write it differently. The limit for n till infinity of the sum of xi minus m divided by the square root n sigma is in distribution. The distribution of those converges to the standard normal distribution. Okay, so this is a version maybe you have already seen. And the next step is to generalize this. So what we have seen here is why I've written down this in this strange version is here we have once again, so you can write this as the law converges weakly to the standard normal. So here, if we call those xin, what we have once again is that the law of xn1 plus xnn tends to some kind of distribution n01. And the normal distribution once again has this very interesting feature that if you have two normal distributions, two random variables which are normally distributed, and you sum them up, then you get a new normal distribution with the sum of the expectations and the sum of the sigma squares. So for x1 and m1, sigma 1 squared, and x2, normally distributed m2, sigma 2 squared. And once again, x1 independent of x2. We have that x1 plus x2 is once again m1 plus m2 plus sigma 1 squared plus sigma 2 squared. So having this feature is something very different, very similar to the Poisson case. Summing up independent copies gives us a new member of the family. And this is a feature which we would like to explore a little bit more. And for this, I would like to introduce the notion of arrays. I don't know, somebody of you has already seen what is an array? The notion of array. Okay, so then it's so what is an array? An array is nothing but definition. So what do we have given? We have given a sequence, Kn, of natural numbers. Kn should tend to infinity for n to infinity. So Kn could be n, but it's not necessarily just n. And a sequence xnk for, first of all, we have n in n, and the k's are just from 1 to this kn. So what we have here, so an array means that we have some generations of random variables. For example, we have x1, x12, x21, x22, x23, x24, for example, and then it's growing in this manner. So of course, if in each generation they're independent, and we call this an independent array. An independent array if xnk for kn in 1 until kn is independent. Okay, this does not mean that between generations there could not be a strong dependence, but in each generation for each of the n's. In each generation we have an independent family. Okay, it's centered if the first moment does exist, is finite, and xnk is 0. And we call, well, Sn will be then the row sum. Xk is the row sum. Okay, so the sum over one generation, and it's called normalized if the variance of this 1. Normalized if the variance of Sn, if they're independent, then it's nothing but k from 1 kn of the variances of the xn k sums up to 1. Okay, so this is a more general notion than only sums. Here also should be an n, but we have different kinds of generations, and we always sum up over each of the generations. And we call an array asymptotically negligible. Negligible if we have that the limit and infinity of the max from 1 kn of the probabilities that x nk is greater than epsilon goes to 0. This means fixing for each epsilon positive, we can fix the probability that you exceed in each generation this value epsilon, so you're going away from 0. And if this uniformly goes to 0, then we call this asymptotically negligible. Please? So independence of an array means that in each generation we have, so this is n equal 1. Generation means the n's. The n's are the generations, and the k's are the members of each generation. The independence of random variables? Okay. No. Inside the generations, the members are independent. Okay, so for each n, the random variables composed in each generation form an independent family. They are not independent between the generations. The generations can depend. Well, in general, they do. Okay? More questions, please? So, having this, we get a limit theorem, which is probably the most general, actually, you can get. It's the limit theorem of Lindeberg-Feller for arrays. And what does it tell us? So we started with the Moivre-Laplace. We went over the central limit theorem. And please. no, this is the expectation for each member. Yeah, this is only one member. X and K is only one member. Of course, if we have 0, so if it is a 0, then we can sum up, and summing up 0 remains 0. Individually, there's 0, and summing up, there remains 0 due to linearity. Exactly. So for let we call X and K, and K from 1 Kn. So first of all, what we have independent, centered, normalized, array of random variables. Okay. Always all of them over the same probability space, X and K from omega to R. Then we have two equivalent notions. First of all, we have that for each epsilon positive, we have that ln of epsilon, which is nothing. Okay, let me write it down and then explain it. Kn x n k squared, and here we have that x n k greater than epsilon. This object goes to 0, tends to 0 for n till infinity. And the second thing is the array is asymptotically negligible. And because it's a limit theorem, and the law of Sn tends to the standard normal distribution. So what we've got is a limit theorem which tells us that if we have an area which is asymptotically negligible, this means the probability of each of those members of the array to exceed a value epsilon goes to 0 uniformly, and it converges to the normal distributions equivalent to the case that the cutoff second moment, so this is even the cutoff variance. I will write down what this means. So this is actually, you can rewrite this. Ln of epsilon can be seen as the variance because we're centered. So if we didn't have this, it would be just the second moment, but since we're centered, second moment, but since we are centered, actually this is the variance. The variance of the sum from K1 to Kn of xnk, once again, xnk being greater than epsilon. And if we call this for cutoff in epsilon, nk, and the whole sum as S cutoff in epsilon n, then this is nothing but the variance of S epsilon n. But since we have a normalized scheme, this means that this is equal to Sn. So this means, the first condition means that the variance of the contribution of, for each cutoff for values beyond this epsilon goes to 0. So we have no contribution of any single member of this sum, of this row sum. And this is equivalent to converging to the normal distribution under having asymptotic negligibility. So this equivalent means that if we don't have this convergence to the normal distribution, we will infringe this kind of property, and we will see actually where it appears. So we have arrays, and please, where? Indicator, okay. Indicator, the indicator. So indicator of A of some omega is 1 if omega is in A, pardon, and 0 if omega not in A. No, this is not a conditional expectation. This is just the cutoff. So this is the expectation, and we just look at the values where this is larger than epsilon. All other values are just sent to 0. It's not a conditional expectation. Well, it's not. Well, okay, it's not recentered. That it's just these random variables for all those values where we are beyond epsilon. Otherwise, they're just set 0. This is not the conditional expectation. Okay. Okay, so this is the maybe the most general version of the central limit theorem, and this is actually what I wanted to show you, that if we have no contribution for any kind of a member beyond an epsilon, then we have already the convergence to the normal distribution. Because in the next step we'll look for generalizations of these, and these are infinitely divisible distributions. Infinitely divisible distributions are also limit distributions of limit theorems, but these limit theorems are, of course, weaker. They're not central limit theorems, but in the best case, they're local limit theorems. So I will make some space here. Pardon? Variance. Yeah, because this is 1. We are in the case of a normalized array. So writing this or not doesn't matter, but writing it just gives us an intuition what it means. So the next step, so we've already seen that if we have a Poisson distribution, a random variable with Poisson distribution, and two of them, and they're independent, and we sum them up, we get another Poisson distribution. The same thing for the normal distribution, and we'll just generalize this kind of concept. So a distribution mu is called infinitely divisible if for any n and for any n and x is mu distributed, there are x1, xn, so there are random variables, x1 till xn, they are independent, they are identically distributed, such that x in distribution is x1 plus xn. So we have a random variable, And in some sense, for any given n, we find independent copies such that the sum of these independent copies is just n. It just gives us a distribution mu. So in terms of the convolutions, this means for each n, there exists some kind of, let's call it nu n distribution, such that nu is nothing but nu n. So we have, for any n, we have find a nu n, which is just the n-fold convolution of these distributions. So we can write this nu n. So this is just the n times the n times the nth convolution power. So if you just n times convolute the same thing, it's nothing but as writing down a shorthand as the power. Okay, so but you can stick to this if you're not familiar with the convolutions. And this is something we will actually explore a little bit more. So a distribution mu is called infinitely divisible if we have this. For any n, we find independent copies with another distribution. We call it this distribution nu n. Such that summing up these independent copies gave us in distribution this distribution back. Okay. They are identically distributed. Yeah. So nu n distributed. Yeah, independent copies of each other. Okay, so for example, so okay, I know this is an abstract concept. Example. So let's look at some value c. It could be a vector or a real number. Let's call it first a real number. And we look at delta c. This should be. So what we are looking for are, and we have n, when we fix n, we look for n independent copies such that we can sum them up and we get delta c. Or in other words, we have some variable which is constant c. We're looking for n copies of something which we sum up n times in order to get c. So what should this something be? Pardon? Yeah, of course. So absolutely. So you're right. So this should be c divided by n plus c divided by n. You're right. Sure. So if this is a random variable, of course, these are also random variables. And we're summing them up, and this is n times, of course, and then we get it back. So this means the Dirac in C has the nth convolution root, and this should be is nothing but delta c divided by n to the convolution power. You're right, absolutely. So this is not so complicated. If you have something, you chop it into n equal parts, you sum it up and you get it back. Okay, so the next case is just the normal distribution, which we already had talked about. So just using the property we already have seen, that summing up two independent copies, we get another normal distribution. We can just make it backward. So for instance, if we have y1, which is normally distributed with m1, and here we have some positive definite covariance matrix, so can be or sigma squared if you like to, and the same for y2. And we assume also that they're independent. Once again, I just repeat this. They're normally distributed with m1 plus m2 and a1 plus a2. Okay. So if we fix now n, so what we would like to have, we have n, we have x, n, ma given. So what should be the good relation to get back with n independent copies x? Well, it should be just the expectation should divide it by n, and here we should also divide this matrix by n. So what we get is if we have xn k, and or xnk being just normally distributed with 1 over n m, and here 1 over n a, the sum of those k from 1 till n is just once again back m a distributed. Okay, so okay, once again independent. Okay, so this is exactly just using what we have here, and just maybe I should write it down. This can be seen maybe in the easiest way. Well, you can actually calculate these kind of things. You have to convolute the distributions, the densities, and things become actually quite involved. You have to work a lot, and in the end, it works out. I think maybe the easiest way to see this is via the characteristic function. If you're not familiar, characteristic function is nothing but the Fourier transform of distribution. I will give a short introduction to this in the afternoon if you're not familiar with this. So, okay. The characteristic function gives us a function associated to a probability measure. So if we have the characteristic function of a random variable, this is the characteristic function of the distribution of this random variable. Then if we have some, maybe of x, of u being in Rd, we have here, this is an exponential, once again, this is something very important. We have I, m, u, and here with minus 1/2 a, u, u. So this is the inner product in Rd. So this is nothing but I from 1 till d, xi, yi, and okay, the norm associated. Okay, so you have the inner product of those, and this is a very general form, and this exponential shape just allows us to get back this uniform, this infinitely divisibility. It's something which is very, very important. For example, in order to check this, first of all, if we have the sum, the characteristic function of a sum of independent things, then it becomes the product of those. And if it's the product of those, then we can see that we have exponential of a product of things. This means we sum up in the exponent, we sum up here, so we have linear things here. So linear thing and linear operator in M and a linear object in A. So what we can do is just we sum up M1 and M2 and we sum up A1 and A2. So, but okay, maybe something after this afternoon session. So maybe to finish, a last example, which is will be absolutely crucial. Where are we? Last line. In Rd. Exp. Here. AU, comma U. AU, comma U. This is, okay. A is a matrix, U is a vector in Rd. And so we have And this is the inner product of those vectors. So this is a vector, and this is a vector, and the inner product in this sense. Okay? More questions? Please, don't hesitate. So, okay, what we had seen is that for the Poisson distribution, summing up to independent Poissons, we get back a Poisson. And this can be done in the same way. So if we have pi being Poisson distributed with some intensity lambda, then the xn case and should be also independent, identically distributed, and they should be Poisson distributed with lambda divided by n. Okay, you can check this. So the most important example we will need in this lecture is actually the following. If we have a Poisson distribution with some intensity lambda, and we have a family of zeta k's, now, or so can be in RB with values in R or in RD, independent and identically distributed, with some distribution mu. Then we define a new random variable, C of omega, is just defined as k from 1 till pi of omega. Of course, it's a random variable. And here we have the zeta k of omega. So what we do is, for each omega, we look how large the Poisson distribution is. And of course, well, we assume that pi is independent of this family, zeta k. Then, so for each omega, we look how much is our Poisson distributed random variable. And then we sum up until then these independent things. So if we have a Poisson distribution, what we can see or how we can write this, get this back, is that pi is nothing but summing up ones. So we can, so pi of omega, k from 1 to omega. So this is, okay, just to get back what this means. So what does it mean? This means the mu in this case would be just delta 1. So just, we're summing up ones with a probability 1. Here we have replaced these ones by an independent family of random variables, and what we can see is that this is also infinitely divisible. So this can be done via the calculus of the characteristic function. Amit, do you give me 4 minutes, or do you? Okay. So in 4 minutes I can calculate this. It's a very, very important calculation, so I think it's good to have it seen in the first class. So the characteristic function phi of this random variable u, for u in Rd, well, by definition, it's nothing but e to the I, and here we have uc. Okay, this is the definition. If you haven't seen it so far, we'll talk about this in the afternoon. So, okay, once again, the expectation, e to the I, u pi zeta k. Okay, so what do we do first? First, we have two independent things. The best thing is to condition on which values takes pi. So we can use the total probability theorem. Pi takes values from 0 till infinity, so we have maybe L from 0 till infinity, a to the e to the I u L, k from 0 till L, zeta k. Well, first of all, in the pi is here, conditioned that pi is L, just to recognize the pattern, p equal to L. So we know that pi is a Poisson distribution. And we know that pi is independent of the zeta, so we can just plug it in and we can just forget about this condition. L from 0 till infinity, the expectation of e to the I u k always from 1, pardon, from 1 until L, zeta k's, times, and here we have already the Poisson distribution with intensity lambda. This means lambda to the L factorial, e to the minus lambda. Okay, so this is something also very nice, because this is e to the something of a sum. This means we have a product here, but the product of something which is, first of all, each of those members of the zeta case are independent, and they are identically distributed. So this means we can rewrite this as L from 0 till infinity, e to the I u. We can just take zeta 1, because zeta 1 is distributed as any one of those. And this is, they're multiplied k times lambda to the L factorial e to the minus lambda. Okay, and here we see already a pattern. So this already looks very familiar, very similar to a Poisson distribution. Here, so, pardon, L time, should be L, of course, sure. Thank you. So, we can just plug it in. L from 0 till infinity, expectation. So this is this here is nothing but the characteristic function of zeta 1. U zeta 1, the L, maybe lambda to the L factorial e to the minus lambda. Okay, and so what does it give us? This is an exponential series with e to the minus lambda. Exp, okay, maybe I should write this in the exp minus lambda plus, and here we have, what is this? This is nothing but the integral e to the I u y mu dy. So this is nothing but the distribution of the zeta case times lambda. Okay, and now reordering just gives us exp to the integral e to the I u y minus 1, and here we have lambda mu dy. Which one? From here to here? This is nothing. So, Joe, we can just pull this out. There's nothing but this here. And this is an exponential series. So this is nothing but e to the x is so we use this formula. That's everything. Very elementary. Okay? And what we get is this formula. And this formula actually is the core of the characteristic function of all of those infinitely divisible distributions. And we will see this next time. This will be the Lévy-Khinchin theorem. Other questions now? Everything clear or everything unclear? So if there are questions, please in the afternoon or whenever, just approach me and we talk. Thank you. The uniform distribution. So you just calculate it. So for example, if you have what you see is okay. You look at well, the uniform distribution just means that you have the set and you have a flat density. And what do you do if you have, for example, uniform distribution in 0, 1? And you convolute it with itself, it becomes these kind of nice splines. And this is absolutely not uniformly distributed. So this is actually how these splines are actually constructed. Wait, maybe I get the... Okay, how to prove that it's not? Okay, first of all, if you, this has to do with the shape of the characteristic function. If what you need in order to get this, you need some kind of exponential form. If you don't get an exponential shape of your characteristic function, then there's no way to get this. So you get some kind of functional relationship, and this is equivalent that something is an exponential. More questions? If not, then I think. Of course, sure. Thank you.